Okay, good morning, everyone. Welcome to the first day of the workshop week. So we have assembled here this week to review the most recent developments in the field of fast transients. And we begin the day by requesting Professor Rajesh Gopakumar, who is the Director of ICTS, to give his welcome address and also give an overview of ICTS. Over to you, Professor Rajesh.
Thank you very much. My welcome to all of you. Some of you may have been here last week as well for the school part of the activity and already maybe gotten to know a bit about ICTS, but there are some others who are joining right now. So anyway, I'll give you a sort of a brief overview of the institution you're at. And hopefully you will find this a very conducive place for your activity. I'd also like to thank the organizers for putting together this important meeting. So this is a picture of ICTS as it was around 2018 when the buildings were constructed. This is a more recent picture in which you can see the trees have grown, the buildings are much the same. Now there's actually more construction happening at the back over there, as you might have seen, near the cafeteria, which is a new hostel complex of ICTS. That's coming up. This is the cafeteria itself. You have probably had your meals there. The guest house where most of you are staying is here. We are currently in this Ramanujan auditorium, and this is a bigger Chandrasekhar auditorium. This is the academic block, which has the offices of the faculty, students, postdocs. There's a library building here, which is a very interesting place, which I invite you to just go and see, or even maybe if you want to spend a little time, quiet time to yourself, that's a good place to do that. But anyway, yeah, so this is actually a watercolor of the library building, which one of our visitors actually made, and so we are happy to highlight it. But what I wanted to tell you about was the institution as such. And so ICTS is a center of the Tata Institute of Fundamental Research. TIFR, as you know, has now multiple centers. NCRA is one of them. And each center has its own mandate. Like NCRA, the mandate is, of course, primarily to run the GMRT. But ICTS also has its mandate, so all of the centers of TIFR, whether it's in Pune, Hyderabad, Bangalore, have their research component, which is, of course, integral as part of TIFR. But the special mandates at each center vary. And at ICTS, the idea is to have programs and workshops like this, because in India, we have not had a center like the US has the KITP, and in Europe, there are many centers like the Newton Institute or the Galileo Institute and so on. So the template for ICTS draws on many of these institutions, but with innovations for the Indian context. So we have programs, and we also have an active research faculty, and we do a lot of outreach, and these three things we try to interweave with each other. So we have the programs are also in a very broad range of topics, include physics, like here, physics, astronomy, astrophysics, cosmology. I include all of that in physics, maths, computer science, quantitative biology, climate sciences. So it's quite a wide canvas, and we now have programs, as I'll tell you, almost essentially the year round. So 35 to 40 programs per year. But first, a bit about our research. This is a collage of some of our faculty at ICTS. And these faculty have their strong core strengths, but we don't have any departments. We have people in the physical and mathematical sciences. We have about 35 to 40 faculty. We have an active PhD program with about 120 students, and postdoctoral program as well with about 30 postdocs. In the mathematical sciences, we have dynamical systems, PDE, climate sciences, algebra, geometry, mathematical physics, probability, theoretical computer science, which we have just started, and quantum computing. And in the physical sciences, we have astrophysics, of course. We have a very active group here working on gravitational waves. And I think Professor Ajit, who is the Dean also of programs, might have come last week to welcome many of you. So he together with several others, working in different areas, and not only gravitational waves, but other areas as well. You might recognize Rajaram Nityananda, former director of NCRA, who also comes and spends time at ICTS. Condensed matter, StatMech, fluid dynamics, quantitative biology, string theory, quantum gravity, and quantum field theory. So these are the different topics. Let me say a bit about the programs like this one. As I said, it's a very active set of program events that we have at ICTS. It's in high demand. So we have a lot of programs throughout the year. So how are these programs organized? I just want to give you a glimpse of that. So they are organized by can be organized by anyone. So proposals can be submitted from anyone in the global scientific community, and they don't have to be based in any Indian institution. And this is an open call, and there are 2 deadlines, one in the middle of the year and one in the end of the year, like the next upcoming one, December 31st. And the proposals are usually for programs about 2 to 3 weeks long. And we usually want a pedagogical component in these programs, like you had the school the last week, because one of the mandates, specific mandates, is to train younger people, like many of you, to grow the expertise in specific areas, frontline areas of science. And that's why we insist on the pedagogical component. We do have shorter meetings, about a week or so, which we call discussion meetings, which don't necessarily have a pedagogical component. So as I said, we have about 35 to 40 programs a year. It's a very packed schedule. It's very much in demand. So the number of proposals that we get is about 2.5 times as many as what we can support. So so there's a rather large, rather small acceptance ratio, these are good proposals. So it is very competitive, because especially since we cover a large set of areas. And we have about 3,000 external participants and a large international involvement in these programs. So, so currently the call for proposals, I mentioned December 31st is a deadline. That is for program, if you want to organize a program here between March 2027 and April 2027 and September 2027. So about 1.5 years in advance is the sort of, so the calendar till March 2027 is completely full, at least for the longer programs. We do try to accommodate the smaller discussion meetings in between. It's fair to say that I think these programs have created a kind of a hub, a kind of an aggregator for scientists to meet and to sort of form new collaborations, come up with new ideas through brainstorming at these meetings. So a lot of research publications have come out from the programs. And again, here I appeal to you that if there are publications that you feel the meeting at ICTS, or if you did some of the work here or originated here, please acknowledge ICTS. The program office will tell you give you a sentence if you can add it to the acknowledgements. That will enable us to keep track of the publications and, of course, use it with the funding agencies to continue support for these programs. So that, as you can imagine, is very important. So we have fairly impressive numbers, and that's thanks to the sort of the cooperation of the members, the participants. So please do that. The other tangible outcome are the talks that are recorded. The talks at ICTS are on this YouTube channel called ICTS Talks, which has now actually nearly 10,000 lectures. and about 70,000 subscribers. So these numbers need to be updated, 7 million views, etc. So it's a very popular channel because there's a lot of very rich material there. I mean, even if you didn't get an opportunity to participate in person in these meetings, your friends can actually watch the videos, either live streamed or watch them the recorded lectures later. And you can also go back and watch these to refresh your memory or to kind of build on something that you may not have understood at that time, as well as all the past lectures. And we've had a number of programs in astronomy and astrophysics. So you can watch some of the previous meetings as well and get a sense for, get some, especially for the younger students, learn some new topics. So this is a good resource, which I would recommend to you. This is just to give you a sense for the kind of, some of the smaller meetings we've had, which are aimed at creating roadmaps for Indian science. So in fact, the Future of Indian Astronomy meeting, which came up with a 10-year vision for astronomy in India, was held here as a brainstorming meeting about 2 years ago. Several others, and you can read the titles here, which are meant to sort of generate interest in new areas in the country. There are also schools, and again, we have been running since 2013 as annual school on gravitational wave astronomy, which has been very popular, and I think many now, almost like a whole cohort of students have gone through these schools and become researchers in this area. So that's an important training activity that we have conducted. There are similar schools in many other areas, some of which have been running for more than a decade. And so that's something that I think is also a contribution that has made an impact. There are also special lectures on our webpage, which you can watch by various distinguished scientists in the Chandrasekhar series for the physical sciences and others in mathematics, computer science, etc. Finally, outreach. We do a lot of outreach. We have public lectures and so on. There's an annual, not annual, a monthly Copy with Curiosity talk, which we do at the Nehru Planetarium in the city. And it's once a month, and it's addressed to the general public. There are also interactive science science exhibits that we have done. And finally, we also do a lot of science pedagogy in terms of working with some of the schools around us, and also working to encourage mathematical talent through a math circle network. So there's a lot of things here that we do, which you can also see on our webpage, and again, watch some of the public lectures on a variety of topics. So any topic you might think of, I'm sure you'll find an ICTS public lecture. So that's more or less what I wanted to say right now. So thank you very much, and I hope you'll have a productive stay, and especially younger people, I hope you will interact very closely with the lecturers. The whole point of staying in a campus is that you can have all your breakfast, lunch, dinner together, and so you can catch the speakers, even if you don't ask questions in the lecture, which you should. You can always catch them after the lectures and over the lunch or dinner, breakfast, and try to learn that way, and of course, amongst yourselves as well. So I hope you'll all actively engage with the meeting and come up with new ideas. So thank you very much.
Thank you, Professor Kumar. All right, we now get started with the program for the day. The first speaker is Vikram Ravi, who's going to talk about DSA 2000. This is an invited talk, and this is also an online talk. So Vikram, just let's know. take it away when you're ready.
Hi everyone, I'll just test my audio and make sure it works okay.
Can
you hear me okay?
Perfect.
Great. Let me just share my screen then. Here we go. Can you see this okay?
All good.
Great. And let me just hide a couple of things here. Great. Well, hello everyone, and my apologies for not being there with you in person. I hope those of you who were at the workshop last week had a very productive time, and I'm looking forward to telling you about the DSA 2000. So I'm Vikram Ravi. I'm a professor of astronomy at Caltech. I'm speaking to you from Los Angeles, and yeah, I'm going to tell you about this project that we think is really going to change the way radio astronomy is done in the coming years, and hopefully you'll see why. So the DSA 2000, first of all, is going to consist of 1650 6.15 meter antennas. So this is equivalent in collecting area to a 250 meter dish. For those who have been following this project for a few years, at one point we were planning on 2005 meters, but we've optimized for both sensitivity while maintaining survey speed to get this somewhat increased collecting area with fewer dishes. This gives us at zenith the same sensitivity as FAST. The array will be sited in a valley in Nevada, and we'll basically see the whole sky north of deck of minus 38 degrees, with interferometric PSF of about 2.7 arc seconds in the middle of the band. So DSA 2000 is not just a fast transient telescope, although fast transients are a major part of what we do. Within this 0.7 to 2 gigahertz band, it will always be imaging. It'll always make images of the sky, both in the continuum as well as on spectral lines, with full polarization, and providing the capability to detect slow transients. But it will also simultaneously search for both fast transients as well as pulsars. It will also be able to time a few pulsars within the beam at any given time as well. All data will be public. This is a condition of our funding, and they'll be made available in an archive with no proprietary period. We expect to be starting our major surveys in 2029. So if you sort of follow things like the SKA, and maybe some of you have been to the GMRT or other radio telescopes, you'll know that the site is really important. It's important to have a radio quiet site with an excellent RFI environment and an excellent sort of soil conditions, and in some cases atmospheric conditions as well. And we think we've found the best site, certainly in the continental United States, for this. Permitting on the site is underway, and we expect to start construction late next year. This place has some very interesting sort of bits of history. One of the nearby highways is called the Highway to the Extraterrestrials, because this happens to be, not near, but not all that far either from Area 51 in Nevada as well. So the telescope will conduct surveys over 5 years, over a 5-year prime mission. And in doing so, it will spend about 65% of its time on this cadenced all-sky survey. This will be sort of revisiting patches of the sky over and over and over again. It'll spend something like 10% of its time on gravitational wave follow-up in deep fields. This is following up neutron star mergers, for example, detected by ground-based gravitational wave detectors, hopefully LIGO India, by the time this thing comes online, as well as spending about 25% of its time on pulsar timing array science. So this is timing millisecond pulsars to search for signatures of gravitational waves. This is an approximate breakdown and may well evolve, but this is the plan as it stands. So to put this in context, the 2020s really is the decade of surveys. It's sort of a decade where all around the world, telescopes are being built that will really kind of revolutionize the way that we don't just see individual objects in the sky, but the whole astronomical sky. So you'll all be familiar with at least some instruments on this slide, like the Rubin Observatory is coming online now, and the optical, the Euclid Space Telescope is already taking observations. We hope that Roman will be launched in a year or two. And there are a few others as well. And DSA 2000 really fits into this kind of context pretty neatly. We really think that we're the radio equivalent of Rubin. At one of our early reviews, Matthew Bales, I think, told us that he thought that the DSA 2000 could keep all radio astronomers worldwide busy for a decade. We hope that that is the case. Oh, there we go. And I just want to emphasize again that the data that we produce will be public with no proprietary period. This includes science-ready data sets, both in the continuum and spectral lines and polarization, with photometry at kind of every sort of detected source in the sky, together with SEDs, light curve fits. We expect to be also making sort of metadata such as alerts and so on public for pulsar and FRB detections as well. And the public archive that we produce is under development by Schmidt Sciences, who have so far been our primary funders. This is the philanthropic arm of Eric and Wendy Schmidt, Eric Schmidt being the former Google CEO. We will also, as part of the project, maintain a commissioning and science verification archive to kind of enable us to bring the thing online. So why are we doing this? The science case that we have is pretty broad, and to give you a sense, within these sort of four themes, for example, in multi-messenger astronomy, we're going to be following up the mergers of neutron stars to detect the radio afterglows, as well as directly detecting gravitational waves via pulsar timing. Our H1 observations will provide detailed information on galaxy kinematics, gas contents, and so on. For example, the THINGS survey, which for several decades led the field with the VLA, we will do that, but improve it by a factor of a few hundred, just in galaxy counts. In terms of the dark sector and strong gravity, we expect to have various probes of cosmology, such as being a very competitive strong lens finder for time delay cosmography. We also expect, via the discovery of many pulsars, to be able to find relativistic binaries to test theories of gravity. And then in the dynamic radio sky, we expect to find many FRBs and many slow transients. For example, our detection forecast is something like 10 to the 5 FRBs over the course of the survey, each localized to better than half an arc second, together with 20,000 new pulsars and 10 to the 6 slow transients. This few to a few tens of individual GW sources we predict via pulsar timing array science. This is all enabled by the very high survey speed of the array. This is a somewhat outdated plot. The latest estimate pushes this a little bit to the right to be equivalent to SKA mid. To emphasize some of the science goals, our FRB science goal is really focused on the idea of determining the distribution of matter around and in between galaxies with FRBs. So, for example, with this large sample of FRBs, we expect to be able to place incredibly accurate constraints on the effects of feedback during the process of galaxy formation on the baryon distribution. This is a major uncertainty in using relatively small scales for cosmological purposes, for example, from galaxy redshift surveys or from weak lensing studies. Indeed, when we combine our data with Euclid weak lensing data, we expect to be able to improve constraints on the sum of the neutrino masses. I'll emphasize that the fact that neutrinos even have mass is probably one of our clearest signatures of physics beyond the standard model. And so we're very excited with what we can do with a large FRB sample here. On the pulsar side, we expect to detect many new pulsars, but we'll have a real focus on finding relativistic systems to enable us to test theories of gravity across a whole range of gravitational potentials and curvatures. Just for completeness, via pulsar timing, we expect to localize a few tens of individual sources within the stochastic gravitational wave background. Evidence for the background has been presented by several pulsar timing arrays, and when we come online, we will be the major telescope worldwide for pulsar timing array science. A good way to think about it is that, in fact, our motivation at the very start of the project was really to replicate kind of Arecibo and or fast sensitivity, but be fully steerable and dedicate significant time per year to pulsar timing science. So the data products sort of are pretty detailed in their nature, but one thing to really emphasize here is that, again, we're not just an imaging telescope, we also do fast transients. We're not just an FRB telescope, we also do imaging. All these data products are created all the time and commensally, meaning they're all made together. The images will be science ready in the sense that they should look like optical images of the sky. And this is really enabled by a few things, including the fact that we have a lot of antennas, as well as a back end that we call the radio camera. The commensal pulsar and FRB search is enabled by a back end we call the chronoscope, and there will also be a pulsar timing back end. So moving on now into kind of where the status of the kind of design is at the moment. I'm going to present some kind of refinements we've made to the design in the past year, but in doing so, I hope to also just give you a sense of what we're actually planning to do overall and highlight some of the key technologies. So one thing that we've realized is that it's likely more efficient to implement a variable depth and cadence survey rather than simply covering kind of all the visible sky with fixed observing time and a fixed number of epochs. So one concept for such a variable depth and cadence survey is shown here, where we end up having, over 5 years, 7 epochs in basically the northern Euclid sky, as well as the galactic plane and bulge, and then something like 4 epochs in the region of the sky where we're most sensitive, this is close to zenith, and then a reducing number of epochs as we go away from zenith. And so the logic here is that we want to reach the source confusion limit in our stacked images efficiently. And once we reach that, we don't really want to integrate further, because for much of the extragalactic transient science, it doesn't really matter where you look, right? That's not true, of course, for the galaxy. So for the galaxy, we're interested in galactic transients. We're also interested in doing this commensal pulsar survey, which requires not just discovery, but also follow-up timing. And so we expect to do that via a dedicated extra number of epochs on the plane and the bulge. Another design refinement is the, let me just pause this one sec, is the way that we've optimized the configuration and infrastructure. So our array configuration looks something like this. Now, why is there this little sort of spike there and this strange cutout here? Well, this is the boundary of the site that we have. And so there's some really amazing work by Josh Albert in Leiden and collaborators to try and find a way to take sort of idealized configurations made by Dave Woody here in the Owens Valley, and then adapt them to the site that we have, as well as all the various constraints on the site, like sensitive plants and areas where animals might make their homes, sensitive cultural artifacts, and so on. Try to adapt the configuration to be minimally impactful on all these site features, while maximizing both the PSF fidelity, meaning reducing the side lobes, and also sharpening up the main lobe of the PSF as much as possible. And so this optimization was done, and it results in a PSF that has sort of remarkable mid and far side lobes relative to what we do if we did something sort of more naive than this extensive optimization. You might find it fun to scan the QR code and take a look at our ArcGIS collaboration site. This sort of shows via various layers, locations of antennas and so on. I'm not sure if it's up at the moment actually, but please feel free to try it out. The other thing that we've done is we've kind of figured out how to best place all the infrastructure pieces. So the idea is that on site, we really will have very little hardware. This is one concept of what it might look like, where on site, this building is used to stage the antenna construction, and then it disappears when antenna construction is done. And we're left then with just a few buildings, a few up there for maintenance, and then a couple of basically shipping containers that host the digitizers and channelizers and the networking hardware to put the data onto backhaul fiber. And so it's a really very lightweight site at that point. Let's see, can I flip through? There we go. And then the rest of the what we call the radio camera and the chronoscope will be implemented on compute hardware about 110 kilometers away in a nearby town. The radio camera is really a concept that's also pretty unique to this telescope. Typical interferometers like the VLA or the GMRT have images that really require visibility-based deconvolution to create the images with high fidelity. What the large number of antennas together with our calibration scheme enables is a deterministic stream processing pipeline that directly creates images. To give you a sense of how the number of antennas makes a big difference, you can kind of see here just what our project scientist Fabian Walter would look like when sampled with different arrays, and sort of with no post-processing done, no clean, for example. And you can see that when you get to 2,000 antennas, in this case, artifacts, at least visually looking on the screen like this, basically disappear. And so, of course, quantifying what it means for artifacts to disappear depends on your model for the sky as well. And so there is a significant forward modeling effort based on real sky models, calibration errors, the PSF, errors in the sort of beam shapes and so on, that we're using to try and quantify just what errors we can tolerate given the science we want to do on the real sky. For example, if we want to reach a confusion limit in some percentage of the sky, what errors are tolerable? Now, the chronoscope is, as I said before, the back end that we use to detect FRBs and pulsars. And so this is kind of it's big. The idea is that we want to use about a quarter of the band to search for pulsars and FRBs in real time. It has to be done in real time because, like with the radio camera, where we can't really store the visibilities due to the enormous data volumes, here we also can't really store the search mode data because of enormous data volumes. We expect to do real-time commensal sort of searches for dispersed pulses in 6 million beams that tile the field of view. Now, this sounds like a lot, but just for context, this is about 3 to 6 times that of what the VLA RealFast system searches, and something like twice that of what ASCAP Krakow searches. So not really very far away from existing systems, because of course, when you think in the image plane, a beam is a pixel. And if you're doing image plane searches, you're searching a lot of pixels, right? And you can say that you searched 6 million beams. The key difference between what we're doing and what instruments like ASCAP and the VLA do is that we cannot de-disperse the visibilities and have a much smaller problem than if we de-dispersed the pixel data. It's kind of equivalent because we have a lot of visibilities as well. So it just becomes a giant brute force compute problem in many cases. If we can solve this, we expect to see sort of 10 to 20,000 FRB detections per year. And these will come with public alerts. We also expect to be performing near real-time commensal searches for pulsars in the 0.1 millisecond data. This will include targeted searches towards continuum sources from our own surveys, as well as blind searches in a limited number of beams at a given time. The pipelines that we're putting together are expected to be fairly standard, nothing too unusual here. I don't need to dwell on this too much at this point. Let me also say that one reason why we are able to achieve the sort of sensitivity that we expect at moderately low cost is the innovations that have been made in the antenna and receiver design. The antenna has to be extremely highly performant in a few different ways. To make the radio camera work, we need surface accuracies that are something like lambda over 200, meaning RMSs of better than 1 millimeter on the surface, which is, strange for a telescope operating at 20 centimeters wavelength. Equivalently, we also need the pointing accuracy to be better than an arc minute, which also places constraints on gravitational deformation, how well the feed is located, manufacturing QA, and so on. We also need to minimize ground pickup and crosstalk, for which purpose we have this shield around each reflector. This is similar to what Arecibo installed. And then the other thing is that a real bit of kind of magic in our process is the fact that we're also able to achieve receiver noise temperatures that are basically as good as cryogenically cooled systems, but at ambient temperature. And so this is now being demonstrated. It's achieved by a combination of really excellent transistors, as well as a well-designed input matching network. And the resulting sort of prediction is a TSIS divided by aperture efficiency of sort of, better than 30 Kelvin within a few tens of degrees of zenith. This is TSIS divided by efficiency, not just TSIS. We're beginning to validate some of this at a test array in the Owens Valley. These are still 5-meter dishes. The 6.15 meter dishes are currently being built in Germany. We're also testing in the Spring Valley site, the site that we're hoping to begin construction on next year. This is just a reflector placed in the back of a truck. We drove to a particular private property there. Early measurements of TSIS are very promising. I'll point out that the particular spectrum analyzer used here has a very bad resolution bandwidth, which means that these RFI signals, which largely originate in space, kind of leak well across the band. But you can see that in the good parts, we're getting 20 Kelvin on sky, which is gratifying. One thing I want to really point out before finishing is that in the last sort of 4 to 5 months, we've really become aware of and are now fully targeting the use of these new rack-scale compute hardware systems from NVIDIA. AMD also has an equivalent. We really think that these are revolutionary for large radio astronomy arrays. Our current plan targets about 6 exaflop of processing at FP8, which can be done in just 5 racks with a power cap of well under a megawatt, something like 600 to 700 kilowatts, which is absolutely incredible. These racks are basically sold as racks. They're not sold as individual sort of cards or even individual server units that can be plugged in. The vendors sell racks that are fully integrated. For example, all the GPUs in the racks are connected via sort of proprietary data links that effectively enable them to act like one big GPU, where all the memory in the entire rack is addressable from anywhere, both on the CPUs and on the GPUs. And so we're currently benchmarking the implementation of sort of the key parts of the radio camera and chronoscope pipelines on this sort of hardware. The initial results are very, very promising. So yeah, this really, we think, it brings this the really ambitious kind of goals. For example, in the chronoscope of doing these searches in 6 million beams, in other words, with full sensitivity and full field of view for FRBs. With this sort of hardware, we really think that it's very achievable. Just to finish up, so when we're fully operational in 2029, we expect that this will be the most powerful gigahertz frequency telescope worldwide. The key sort of technologies that make this possible are the radio camera and chronoscope developments on this new hardware and the highly performant antenna and receivers. We're also exploring a complementary low-band system to accompany this, to make use of the same infrastructure, where in that case, the main science goal would of course be EOR science. With the dishes, we expect to do transformational science and multi-master astronomy, cosmic history, dark sector and strong gravity, and the dynamic radio sky. We anticipate a very rich yield of fast transients, and all the data that we produce will be served publicly with no proprietary period. And yeah, leave it there and happy to take questions.
Thanks, Ravi. Very interesting indeed to learn about the DSA 2000. Questions from the audience? Meanwhile, those online, if you have questions, please type your questions on the chat window and I'll come back to you.
Hi, I'm Yash. So I have a question, like since the disk array are very compact, will there be shadowing effect for low elevation sources, or are they sparse enough to?
The array is not so compact. The configuration, let me just focus on this for 1 second. The dimensions of the site are something like 19 by 15 kilometers. So we're only placing 1650 dishes in that area. The typical spacing is a few hundred meters between antennas. That said, we do have some short spacings as well, where shadowing will be an effect. But the number of baselines, for example, under 50 meters is in the sort of several tens, and that's all.
Questions from the audience? Questions online? Okay, not let's thank Vikram again and move on to the next speaker. Thanks, Vikram, a lot. Thanks a lot.
Thank you. Thanks.
Right, our next speaker is Kaustubh, who's going to talk to us about the Mere Trap project. Whenever you're ready, Kaustubh.
Right. I hope you all can hear me. Yeah. So morning, everyone. For those of you who don't know me, my name is Kaustubh Rajwade. I am a researcher based at the University of Oxford. So this morning, I'll be talking to you about the MEERTRAP project. So I'll basically first describe what this project is, and then end with some of the science that has been happening since we went operational about 4 to 5 years ago. So since last week, we have been hearing a lot about fast radio bursts. These are cosmological flashes, radio flashes that we see from all over the sky. And there's a lot of scientific interest in two things. One, trying to figure out what they are, because that's kind of probing some extreme physics that we really cannot manage to possibly do in labs on Earth. And also to try and realize their potential as cosmological probes, because we know they are cosmological. The question is that whether we can really use them to answer some key outstanding questions in cosmology. I mean, since the field kind of kickstarted about, it's almost coming to 2 decades now, there's still some open questions, right? For example, in terms of figuring out the emission mechanisms, there's still a bit of debate on what's happening, right? I mean, are the FRBs coming from the magnetosphere of a very energetic compact object, or are they coming from a bit far away from the compact object, whereby you have a kind of a flare that's kind of shocking the ISM, and that's what's causing the emission of these FRBs. As far as the application is concerned, again, like if one of the key applications we can see is that we're trying to map out, the baryons the distribution of baryons in the universe. And so it's quite important that we not only detect FRBs, but localize them very, very accurately so that we can identify their host galaxies, and also then try to disentangle the different contributions of the different components of the cosmos in terms of like the intergalactic medium, the host galaxy ISM, and Milky Way, and so on, to really kind of literally weigh the universe. And so what we need is that we need to continue monitoring the sky for these things. We need to continue discovering FRBs, and we need to continue localize them. So then the next obvious question is then why not do it with basically all radio facilities that are available across the globe? And so that's what we did, right? So MEERTRAP is a commensal real-time FRB and fast transient detection instrument that's been deployed at the MeerKAT radio telescope. So for those of you who don't know, MeerKAT is a 64 dish radio interferometer. Each dish is about 13.5 meters in size. It's located in the Karoo Desert in South Africa in the Northern Cape. Excellent RFI conditions. You tend to get a very clean band. And the idea is that we are observing commensally. So what I mean by that is that MeerKAT has basically the time on the telescope is allocated to different science goals. And while the telescope is observing, we're using the same data to look for fast radio transients in real time using a compute cluster. So this is the collaboration. So the MEERTRAP project is PI'd by Ben Stappers, is based in University of Manchester. And we have a lot of collaborators from the Max Planck Institute in Bonn, and of course, University of Oxford and the Oxford E-Research Center. But also, of course, none of this would have been possible without the help of, firstly, NCRAO, because they've supported us immensely during our commissioning observations, earlier in this decade when we just deployed the instrument. And of course, our good friends from F4 who help us to, follow up these FRBs at optical wavelengths to identify host galaxies and estimate redshifts and so on. So just a shout out to all these lovely people. So again, I spoke about commensal observing. So one of the key benefits of commensal observing is that you don't have to keep applying for observing time at the telescope to do your science. And so you're using the same data stream that's being used by different science cases or science proposals to look for FRBs. So we basically have agreements with pretty much all these proposals that I list here. These are large survey projects that were allocated a significant amount of time at Meerkat when it became operational in 2018. And you can see that by the time all the large survey projects end, we're going to end up with almost 20,000 hours of observing time on Sky with Meerkat to look for FRBs. So that's a big opportunity to do a lot of interesting science. So I'm just going to go through some of the key observing modes of Meerkat. So the first and foremost is the incoherent mode. So what we do is we are basically detecting power from every antenna that's observing, and then we're just summing them up together. And so that basically creates a single beam that's looking at the entire primary field, or the size of the entire primary field of view of the telescope. But at the cost, you get this large field of view at the cost of sensitivity because you're not coherently adding these signals from the antennas. And so it's kind of equivalent to doing a survey by a single 64-meter dish, similar to the Parkes or the Murray-Yang radio telescope in Australia. But you end up having a rough field of view of 1 square degrees at 1.3 gigahertz. Then, of course, the next mode is the coherent mode, so whereby you can kind of fill up your primary field of view with much smaller but way more sensitive beams, which are the coherent beams, in which case, as the name suggests, you're actually phasing up the array in some sense. So you're actually adding the signals coherently by keeping the phase information. So it does mean that you get a larger sensitivity compared to the incoherent addition, but it also means that you lose a bit of the field of view. So which means that you need a lot more smaller coherent beams to fill up the same field of view if you want to do a much more sensitive search. Now, of course, because of computational limitations, we cannot fill up the whole primary field of view with coherent beams, but we get a rough field of view of about 0.4 square degrees at 1.3 gigahertz with this mode. But it does mean that within that region, we have a much, much higher sensitivity towards FRBs, and which is comparable to like doing a survey with a 100-meter dish, which is quite good. And lastly, we have the transient buffer mode. So I think we have spoken about this last week as well, whereby if the real-time system detects an FRB, it sends out a trigger which saves all the channelized complex voltages for every single antenna at the time of the burst, right? And now the advantage of that is that you can actually then use these channelized voltages to make visibilities, use that to make radio images at a very, very high time resolution, and actually detect that FRB in these images and get a localization out to about an arcsecond or less. And so then that precision is kind of required if you want to do optical follow-up then to identify the host galaxies. And so yeah, so those are the 3 kind of key things for the survey. I'm not gonna go through the details here, but the key thing is that, yeah, we're roughly looking for FRBs in the range for dispersion measures ranging from 0 to about 5,000. Yeah, with anywhere from less than a millisecond to a few hundred milliseconds. I mean, this number here, I mean, this was kind of increased later once we started to find some of these really wide and really interesting long period sources. And so you want to try to kind of cover that parameter space a little bit more so that not you're completely biased against that population. Yeah, so we're using this C++ based real-time single pulse search pipeline called Cheetah. It's basically a prototype pipeline for the current software stack that is being developed for the square kilometer array as of now. And then we're using a machine learning based classifier. So last week we mostly talked about a CNN called Fetch, which is widely used to identify FRBs and other radio transients in telescope data. We are using a similar machine learning classifier called FRBID, which is a slight variant of Fetch. And that's what's being used for any candidates that come out of the single pulse search pipeline. Yeah, so the hardware was actually installed in the Karoo Array processing building on site back in 2018. So this is how it looks like. So we have 65 compute nodes and a head node. Each node processes 12 coherent beams. So we can search for FRBs in 768 coherent beams in real time as of at the moment. You can, of course, increase the number of beams and stuff, but then it's at the expense of probably reduced bandwidth or reduced time resolution and so on. So that's a choice you have to make because you only have limited amount of compute available at any given moment. Yeah, that's just, I mean, honestly, I mean, I used to show this slide like maybe 5 years ago pretty proudly, but when you look at NVIDIA G1080 Ti's in these days, it's pretty outdated GPUs. Given what's available in the market at the moment. But it still does the job for us. And more importantly, we do have some spare GPUs now because every now and then, one of your GPUs, gets fried because of whatever reason. So it's quite important to keep a few. Just from experience, do remember that when you're building a new instrument. The transient buffer system. So as I mentioned before, in the event that the real-time system detects an FRB. So the way it's built right now is that we have these two compute or clusters. One is the filter bank beamformer. So that's where the beamforming happens. So data comes through from the telescope. You get the beamformer, makes these hundreds of beams, which are kind of transferred to the actual mirror trap system through the network. This is where the search is happening. And then if you are getting a detection, it basically sends out a trigger back to the beamformer, and the beamformer immediately freezes the channelized voltages that it's getting from the telescope. Now, if you assume that you always want to save enough data that you're covering or basically that spans the entire duration of your FRB, dispersion is a problem, right? I mean, depending on the DM, you would have, so the amount of data that you will save will depend on how dispersed your FRB is. And so that would mean that if you start finding FRBs at higher and higher DMs, you're going to save a lot of data. And these data can be pretty hefty, right? We're talking about like almost like 10, hundreds of GBs for like, a few seconds of data. So that's kind of not necessarily sustainable if you're getting a lot of triggers because of RFI or various other reasons, and you have to keep cleaning up the disk so that you don't miss new triggers. And so what we did was that we basically built a system where when we trigger and when we're saving the data, we actually cut across or account for the dispersion sweep of the FRB. And so because the value of the DM and all the necessary metadata is already, the real-time pipeline already has that. And so all of that information is actually sent to the program that's actually doing the triggering and freezing the data voltages. And so you can actually do that. And what that means is that regardless of the dispersion measure of your FRB, you're always going to save the same amount of data per trigger. And so what we do is that we save about 300 milliseconds of data at the time of the FRB for every single trigger. And again, it does not only allows you to localize, but it also gives you polarization information, right? And so you can do high time resolution studies and of any FRBs you detect, and also study the spectro-temporal polarimetric properties. So I'll just go through some of the key, some interesting functionalities that you get with kind of a flexible beamforming system on conventional backends. So I mentioned that, so this is an example of like a tile of coherent beams that you can make. But we are kind of flexible in terms of where we can put these tiles in the primary field of view, and also how much overlap do you want between your coherent beams, right? Because you can say that, okay, I can spread out my coherent beams in the primary field of view, which means that you'll cover a bit more sky, but you also kind of risk FRBs falling in these gaps between the coherent beams and where they won't be very sensitive, so you might miss out a few events. On the other hand, you don't want to overlap them too much because then you're just covering a very, very small fraction of the sky. Even though it's very sensitive, but then it's a very small field. So you still lose kind of FRBs, or your rate of discovery will still be low. So you want to play around with that, and which is what I'm showing here, right? I mean, it shows you different tiles and how they'll look like with different kinds of overlaps between these beams. And so you want to go with something that optimizes for sensitivity and the field of view. So typically what we realized is that if we have an overlap of 25%, meaning adjacent coherent beams are overlapping at the 25% power level. That's what basically would give us the best kind of discovery rate for our searches. Similarly, when I talked about flexible tiling, we actually can make separate coherent beam tiles in different locations of the primary field of view, which means that if you have interesting known sources in the sky, right? For example, you're observing something and then you realize, oh, there's an interesting neutron star right now in the primary field of view. Oh, there's a well-known rotating radio transient that I would like to look at. You can basically just on the fly create a set of tiles or just even one beam and just point to that source and keep following it up while that source is in your field. And that's just an example. During commissioning, that's what we did. We placed 3 separate tiles on 3 pulsars, and we got detection, simultaneously detected all three of them within single observation. So it's very interesting, especially for monitoring and follow-up observing campaigns of fast transients. I think we've also spoken at length about optical follow-up for host galaxies, but also I think if we want to figure out what are the progenitor models for FRBs, I think it's quite crucial that we detect some kind of a multi-wavelength counterpart, right? I mean, when we saw this FRB-like burst from SGR 1935 almost 5 years ago, there was a contemporaneous high-energy burst that was seen with this FRB-like pulse. So we do believe that there are these high-energy components to these things, but we're just not sensitive enough at the moment. So there have also been models out there that predict that there should be some kind of a prompt optical emission there as well. Not just that, right? I mean, you don't want to look. I mean, that's just as far as the prompt emission is concerned. But also you want to try to look for multi-wavelength counterparts after the event has occurred. For example, something like an optical afterglow, because that will kind of constrain the progenitor models. Because if you see an optical afterglow after an event, an FRB-like event, that kind of gives support to models like cataclysmic models, like possibly some of these FRBs are coming from some of these violent explosions that happen in the universe. And so with Meerkat, we have the opportunity to get this contemporaneous optical coverage. So Meerlicht is a 65 centimeter fully robotic telescope that's built in Sutherland in South Africa. And so on a best effort basis, it always tries to co-point with Meerkat during all nighttime observations. So what that means is that if we have an FRB in the nighttime, we're almost guaranteed optical coverage with this telescope. I think it's a bit optimistic, honestly, because we've had some issues. I mean, there have been for various reasons, we've not managed to get optical coverage for a lot of our FRBs, but recently we finally managed to do that. We were almost contemporaneous. I think we were, because of some of in the dead time between different observations, we were off by 3 seconds, I think, from the event of the actual FRB. But that still means we can get some nice constraints on like the optical magnitude from potential afterglow that you could get from these FRBs. So now the last bit, I'm just going to quickly talk about some of the science that we've been doing over the last 4 years. So we are a commensal project, and so Meerkat looks at a lot of pulsars, and which means that we get a lot of galactic plane time from Meerkat. And so that does mean that we end up seeing a lot of interesting single radio pulses from neutron stars in our galaxy. And so far we have discovered about more than 110 of these things, most of them very sporadic, rotating radio transients type sources. But we've also seen some very interesting pulsars, like especially the slower pulsars, right? Pulsars with much slower rotation periods than what we typically find. So one is the discovery of the 76-second pulsar, discovered back in 2022, I believe. Yeah, so again, I said we have increased the width parameter space in our searches just because we found this thing, right? I mean, it kind of made us realize that we're probably losing a lot of these wide single radio pulses because we're just not searching for wide enough pulses in our real-time system. And another one, very interesting one, was that recently we found was a pulsar which had a spin period of 17 seconds. So we're starting to really find these very slowly rotating neutron stars and trying to fill up that kind of, I would say, middle to bottom right kind of space in the PP dot pulsar parameter space. And then we also end up finding things like this, right? I mean, this source, we saw it in a single 20-minute observation. It was pretty much booming, extremely bright, saw every single radio pulse from it, got a period, roughly 10 seconds. And this field is observed very frequently by Meerkat, like once every 2 weeks or so. And we have never seen this source over the last 3 years after that. We saw it once in one 20-minute observation, and then we've never seen it again. And so this kind of begs the question, how many of these extremely intermittent and extremely sporadic radio-emitting neutron stars are out there that we're completely missing because we just lack that continuous wide field radio coverage of the sky. So the point I'm trying to make here is that I think there's a big need for high cadence, wide field of view radio surveys to exactly kind of remove these select observational biases that we have and try to find a lot more of these interesting objects there. Coming to FRBs, we so far found more than 80 FRBs. Roughly 30% of them we have triggered on and have localized to arcsecond precision. And the reason for such a low number is that initially the transient buffer pipeline was not fully operational. And also sometimes we do end up missing a trigger depending on the latency between sending the trigger and when the FRB happened. Because sometimes if the RFI environment is bad, we do slow down our pipeline. It does slow down our pipelines, and that leads to us missing the storing of the voltage data completely. But very interestingly, given that Meerkat is so sensitive, we find these very high DM FRBs quite frequently. Very recently, just kind of highlighting one of the key results that have come out very recently, we found this FRB at a DM of, actually that's not correct, it was 2642 instead of 2462. We applied for some DDT time with JWST, and actually, so this is I believe it's a NIRCam image of the field. And you can see that we managed to find this very, very faint source, which we definitely believe is the host galaxy for this FRB. And the redshift we estimate for this is 2.15. So this is the first FRB as of now that we know is, has a redshift of more than 2. So we are starting to find these very, very far away FRBs thanks to the incredible sensitivity of Meerkat. And of course, we have just showing you some interesting kind of dynamic spectra for some of these FRBs. And this is just showing you the power of the transient buffer, because both these sources were seen as single Gaussian peaks in our real-time system. It's only because we had the transient buffer data that we could go down to high time resolutions, right? We're talking resolution of about 4 microseconds here. And suddenly that FRB turns into something weird, into something that has a weird shape with multiple components that show up at different kind of frequency Cs in the dynamic spectrum. And then, yeah, of course, as I mentioned, that we're building this with Meerkat, a sample of FRBs at higher DMs, and which means that if you put them on this McQuart relation that we spoke about last week, which tells you about what the rough redshift would be for an FRB given the extragalactic DM that you see from it or that you measure. And then if you have a big sample that you can localize well enough, then you can kind of use that to kind of constrain this relationship at these higher redshifts. And the only way you can do that is by finding these things with very sensitive radio telescopes. And Meerkat is going to be probably very crucial until these next generation telescopes show up to kind of fill up this kind of parameter space here in the McQuart relation. Then recently we found this very interesting galactic source, single coherent radio burst from it, which was localized to a known thermal X-ray neutron star. which is not known to be radio loud. It basically belongs to a subclass of neutron stars called X-DINs, or X-ray dim isolated neutron stars. People have always spoken about the relationship between X-DINs and radio pulsars. I'm almost done, it's my last slide. Yeah, for the first time it's showing us maybe we have found this missing link kind of transitioning source where showing us an evolutionary path between these different subpopulations of neutron stars. And lastly, we've also started finding repeating FRBs. As we know, it's a very small fraction of FRBs that we see. Mirror-Trap so far has found 2. And again, just an example of like showing some super interesting emission features. So I think I'm just going to end up with my summary. I hope that I have kind of driven home the point that Meerkat is an excellent radio telescope for doing FRB science. And we're starting to find these very interesting, very far away FRBs, which we're starting to finally start using FRBs as some very interesting cosmological probes. And if we combine this data with all the other radio telescopes like DSA and ASCAP, I think, the future is looking very bright. So I think I'll end there now. Thank you.
Thanks, Kaustubh. Very interesting talk indeed. Questions for Kaustubh?
Hey, thanks, Kaustubh, for the interesting talk. So one thing is, so you said that you are increasing the population of FRBs having high DM. So do you intrinsically find those to be more faint or having less fluence?
Not, I can't say, I don't think I can comment on that at the moment, because the problem is that we have found these FRBs with high DM. It doesn't necessarily mean that we have the exact distance to them. So until we actually estimate the redshift, it's only then that I can actually get a luminosity for them, and only then I can comment. So the problem right now is that we have a couple of these sources. They're definitely not, they're definitely on the higher luminosity end based on the redshift that we have. I won't say that they're like something crazy bright. It's definitely consistent with the population. But a majority of these high DM FRBs, we're still struggling with A, identifying the host, and B, getting a redshift for those hosts, just because of the limitations in optical telescope capabilities and also the limited resources that are available. But yeah, definitely something to look at. Thanks.
Hi, Vikram here. So last slide, it seems like FRBs found by DSA 110 are biased towards the higher DM at low redshift. Why is that? And then another question is like, the FRB that you showed in the previous slide is already there, right? The redshift 2.7 or something? Or that's
this one?
Yeah.
Yeah, so
that's the JWST one.
Yeah, so okay, so this, okay, I guess the disclaimer is that this plot is a little bit outdated. And some clarification. So these lines, this is not a fit. It's a model prediction based on the Planck results for different cosmological parameters.
The dashed line.
Yeah, the dashed line, and also these are just the model uncertainties. So you get a bit of a scatter basically. So the expected scatter that goes increases with your high redshift. These yellow points are the Meerkat ones, and the reason they're on the line is because we still don't have an exact redshift for them. So it is just based on if this is the DM, this is the, and that's why you have these error bars that kind of span across your posterior distribution. The DSA ones, yes, those have redshifts, and there's a paper by Liam Connor where he's actually tried to show that by doing modeling that this curve is kind of slightly tilted upwards than what you see from the predictions. And yeah, so that's what it is. So this is not a fit.
So your FRB, what would be the redshift?
So this one now is over basically like here. It's a kind of an outlier here as well. And
even the DM value is smaller than 2,400, right? Or DM is.
Yeah, I mean, yeah, I think, yeah, it's like here somewhere.
Okay.
Yeah. Yeah.
Thanks.
Yeah.
Kaustubh, thank you for the talk. So I was just wanting to know whether Meerkat allows commensal observations of these, and how long you think these observations can go in as the SK is coming in as well?
Well, yeah, I mean, we would like for them to keep us online for as long as they can. until Meerkat is fully integrated in the SK. The problem is that Meerkat is building a new correlator for Meerkat Plus, which is 15 more dishes being added to the 64 dish array. And so they have a completely new network for that, which we're not connected to. So we'll still continue observing with the 64 dishes when Meerkat Plus comes online. So just hoping that the old network still keeps going strong, because you never, things like network issues is a big problem, especially with old hardware. So fingers crossed that we can still continue all the way up to, SK mid. But yeah, I really don't have any solid predictions as to when and for how long we can go commensal. Yeah.
Hello. Hi, Kaustubh. So your current 80 detections, how much roughly on sky time they have resulted from?
I don't know the number on the top of my head.
And are there expectations of some number from your eventual?
So typically our rough rate of discovery, if typically Meerkat is like about 70-ish% efficient in observing. So in a year, roughly 70% of the time it's on sky. And if you assume that, then our rough detection rate is like once a month or something, 1 FRB per month. So it's roughly consistent, but there are so many variables in that. It's a very ballpark number.
But there's some expectations on numbers.
It is very close to the expectations, yeah. Okay. Yeah, on the lower side, it's not higher, but still consistent with the error bars, I would say.
Thank you.
Any questions from the online participants? Any further questions from the audience here? Comments? Last question.
Do you have a new record for Z of 3? Is there a point at?
No, not as of now, no. We don't. I mean, who knows? I mean, we have an FRB that has a DM of 2800, but I have no idea. Like, we haven't done any optical follow-up for that, so really can't comment on what the redshift would be for that. Yeah.
All right, on that note, let's thank Kaustubh. So our next speaker is Scott Ransom, who's giving this talk remotely. And Scott's going to tell us about whether what we think transient is really one. And
hi, everyone. Can you hear me? Can you guys hear me? Uh-oh. Are you not hearing me? Is it possible for you to hear me? I'm not hearing anything back.
You're not audible, but can you please also share your screen?
You said I am audible or not?
Just a moment. I think we're having a technical issue.
I hear you, Scott.
Can you hear me now?
Yes. Yes, we can hear you now.
You can? Is it good?
Yes. Can you please share your screen?
Yes, I will share my screen now. All right, great. Share. All right, you see that?
It's all good. Take it away. Thank
Excellent.
you.
So hi, everyone, and sorry I can't be there. So I'm actually at a meeting in South Africa this week where I have to be here all week. And so I'm just going to give you a short little talk. It's quite high level. It would have probably actually been a better fit to last week because what I'm going to talk about briefly is something I don't think that gets talked about in talks very much. And that is, we hear about all these fantastic new surveys and upcoming telescopes and surveys, such as DSA 2000 that you just heard about, as well as Kaustubh's talk with this amazing transient detection system. But there's a huge amount of effort that goes into getting these systems built and tested to make sure that the transients and pulsars and stuff that we get out of these systems, including the software and the hardware, is really what we think they are. And so that takes a huge amount of effort. And because that effort doesn't usually show up in papers, it's students and postdocs usually who are doing this work. It's not something that we think about very often. So that's kind of what this talk is about. And it's really trying to get people to think about continually testing your system to make sure it's really, really doing what you think it is. So if we're doing a transient and pulsation search, and this can be in the past with archival data, it can be with current telescopes, or it can be with future telescopes. This is kind of the high level information that we need and the things that we think about. So for transients in the radio, obviously we need time and frequency resolution. So we tend to have relatively high data volumes for each pixel on the sky. We need to have well-characterized algorithms that find a weak signal in the presence of noise. And normally in radio astronomy, given the radiometer equation and stuff, the noise that we're seeing tends to be Gaussian most of the time. And that noise needs to be well characterized. So if it is Gaussian, we want to know the standard deviation. We want to know, is it relatively constant in amplitude across our spectrum? Is it relatively constant in amplitude as a function of time? And the reason that's important is because for our algorithms that find the signals in those noise, we do statistics. And the statistics is completely based on the tails of distributions. You were looking at the high signal tails of statistical distributions where most of that distribution is described by the noise. And then finally, when we're detecting pulsars or transients, we want to make sure that we're maximizing the number of real, true astrophysical signals, the true positives, while minimizing the number of false positives and false detections that we get from our software and our hardware. And that last thing, minimizing false positives, is something that we also often don't hear about very much. Almost all modern software pipelines find huge numbers of false positives. And so you do hear about machine learning and stuff in ways of sifting through those candidates. But it's a really, really important part of this whole pipeline, is making sure you don't lose the real things and you get rid of as much of the fake, the false positive things as possible. And so how do you do all of these things and make sure this is all working? And the answer is really very careful testing of every different part of your pipeline as often as possible. And it doesn't stop. It's not that you just test in the beginning. You need to be continually checking that your software and your hardware is producing the data that you expect it to provide. So as some examples, I'm going to show you how we've been developing a pipeline for a new search called the CHAMPS survey. This is using the CHIME telescope, and we use the CHIME FRB backend. So that gives us that time and frequency resolution that we need. So roughly 1 millisecond sampling with thousands of frequency channels across our bandwidth. But instead of searching for FRBs, what we're doing is integrating. We've actually changed the way the beams go on the sky so that because CHIME is looking straight up in the sky every single day, it can't tip. It sees the same patch of the sky repetitively each and every day. And so we've changed it so that the beams can track, so that every day a certain rate ascension and declination will get, once it's above CHIME, it gets a beam that tracks for somewhere between 10 and 20 minutes, that source, while the source is within the CHIME's primary beam. From that 10 to 20 minute integration, we now have a filter bank data effectively of that whole duration that we can then de-disperse. We can create time series. We can Fourier transform those and make power spectra that we then normalize, make sure we understand the statistics, and then we stack day after day after day. We add power spectra together. And what this allows us to do is very, very deeply and slowly over time integrate up very, very faint pulsing signals. And in general, we can get with the CHIME telescope, which is roughly half the sensitivity of the GVT. If we integrate for a month or so, we can get to be the most sensitive pulsar survey for isolated pulsars in the northern sky. But yet we can integrate for years if we want or need to, but only if we don't mess up our stacks and our statistics, because we can't keep the data from every single day. So there's a lot going on with this. So how do we make it all work, and how can we tell if the pipeline is working? And that's kind of what I'll give you some examples of that from this current survey. And I should mention that the paper on describing the system has just been published, and that's the link at the bottom there, the Andrade et al. Paper. And then just to show you what those figures are on the right, we've already found a few new pulsars at the top up here. Hopefully you can see my cursor. Here's the galactic plane. Here's the whole northern sky. This basically is showing the colors show the expected DM. And then here is a strip that we did some test observations, and we found a bunch of new sources that are these colored points, mostly towards the inner galactic plane, even though this is still far in the north, so it's not really true in the inner galaxy. But it is the galactic plane seen right above CHIME. And then at the bottom, this is just a pulsation sensitivity plot that shows how integrating from a day to a month to a year, and this is a logarithmic scaling on the y-axis, it shows how we're able to move down by significant factors if we're able to keep putting these stacks together. All right, so for a stack search, one of the main things that we have is we have time series. We have to take a Fourier transform of the time series and then turn those into power spectra. But some of the things, we make a lot of assumptions about our time series. First off, that in the time domain that we have Gaussian statistics. So this is simulated data, and you're seeing Gaussian random numbers around a mean value of 0 with standard deviation, which is represented by these green lines, that's relatively constant with time. And it's true that a lot of radio data does look like that. But most of you who've seen real radio data know that that is definitely not what it all looks like. There's a lot of other stuff in our data. But if you have Gaussian random numbers and you take a Fourier transform, then square those amplitudes to make a power spectra, you get the Fourier domain, which you're seeing here down at the bottom. And the statistics here, because it's power, there's no negatives, and we've squared two Gaussian random numbers to get this, that gives us a chi-square distribution with 2 degrees of freedom. And we know that analytically, it's easy to do that derivation. And we depend on our tests and our looking for our signals on those statistical properties. We depend on that being chi-squared. So one of the big things that I'm advocating is, when you do this, test for Gaussianity of your time domain data, test that your power spectrum data is chi-squared, and not just in general, but even as a function of radio frequency. Similarly, when you inject a sinusoid in your data, and we're looking for pulsations, if we have Gaussian noise and you inject a sinusoid with certain amplitude, you can compute exactly and analytically what the power in that sinusoid should be. And theoretically, if you have a perfect system, that sensitivity should be equivalent across your whole pulsation frequency band. So a sinusoid of the same amplitude at 10 hertz should give you the same signal as a sinusoid at 700 hertz, for instance, if we're using normal pulsar style sampling. So we can predict that, and we can test to make sure that that's actually what we're getting. So this is one of the things that we've actually done recently, so I'll talk about some of those things. So D-dispersion is a crucial part of it because this is what prepares our time series. You probably know a lot about D-dispersion now. But for this CHAMPS survey, we're doing huge numbers. We have 1,024 beams on the sky at any one time. We're doing this in real time. So a brute force, which is of order of operations n channels squared, is simply too expensive to do that. So we use some of these new techniques like the FDMT, which is a form of tree D-dispersion. There's a whole bunch of these tree style codes that turn the operations count into order n log n. But if we think about going from the time domain up here at the top into dispersed time series down here on the bottom, this is a transform. And these software packages do operations on your data. We cannot just trust that what they're doing is all correct. And we actually found an issue with our system that was not found in the software development's testing. So here's an example of that. So what this plot is showing here, it's showing the power that we get out of a sinusoid divided by what we think the power of that sinusoid should be, given that sinusoids should be, we should get the same amplitude out before and after our transformation and at all radio frequencies. And this x-axis down here is logarithmic of basically the frequency that we're looking for pulsations. The Nyquist frequency, so the fastest frequency that we could possibly detect, is right up here basically at this last data point. So it's up at about 500 hertz. And what I want you to see is look at this dashed blue curve right here. It's right here. In general, we would expect this to be completely flat to the very end. But what you can see is that there's a rollover at the top here. And this is something that I think that most pulsar survey papers have actually ignored in the last couple of decades, because that's, I think, something that most people have forgotten. And that is just the fact that we're summing over many channels, and each channel is not perfectly aligned. So we basically choose the nearest sample as we're adding all those things up. Or even if you're using the FDMT, you're basically weighting nearby channels that correlates nearby samples. That means we lose sensitivity at the highest frequencies. And this is the sine power roll-off that we get. It's related to a sinc squared function. And this is in a nice derivation in a paper by Michael van der Klies clear back in 1988 describes this. But the pulsar community has kind of forgotten about this, but our testing brought that back to our attention again. And even worse, we had a very custom implementation in C++ of the FDMT that we had done a bunch of testing with, and it looked all great. And these are the red curves. Notice the red curve precipitously drops off, and this is a log plot. So at factors of about 4 lower frequency, so we would have lost a factor of 4 of our highest frequencies of looking for pulsars, including the higher harmonics, potential millisecond pulsars, things like that, if we hadn't caught this very, very subtle bug in our implementation of the FDMT. And sure enough, this is my student, Ray. They tested a different Python version of the FDMT in this exact same way, and it follows the blue curves, which is just like what Presto's code does. But these are really subtle effects, and we're doing this before the pipeline is fully up and running to make sure that we understand exactly what's going on. I'm getting blinded by the sun, so I'm going to shift over here so I'm not in the sun. Okay. The next little quick example I want to show you is about red noise. Red noise is something that you hear a lot about, especially for now these searches for slower pulsars and long period transients and stuff like that. Almost all real radio data, for all sorts of reasons, tends to have this low frequency correlated component in our data. So our time domain data do not look like pure Gaussian noise. They look like this red noise data, which looks you tend to be dominated by cubics and stuff like that. When you Fourier transform a time series like that, you get, here's your chi-square distribution at the top, but you have incredibly excess power down here at the bottom. Since we're looking for slow pulsars often, this red noise is a true contaminant of your data. You cannot get rid of it. It means you're less sensitive at these lower frequencies. There's no way around it. So the best thing to do is to try to figure out ways to avoid that red noise in the first place. And I mentioned there are some ways to mitigate. For instance, in Presto, there's a routine called red noise, and this was run on that example. And you can see from the original power spectra, all this power down here. The corrected power spectrum seems to have gotten rid of that. But these data down here at these low frequencies aren't perfectly chi-square distributed anymore. There's more variance, which means we're going to get more false positives. And we have less sensitivity because the noise was actually larger. So this is an example of something that's very tricky to deal with, and the best thing to do is to try to avoid it in the first place. So Robert Main, a postdoc at McGill, who's working on the CHAMPS project, just did a very deep dive into the way that the correlation is working to generate the chime beams. And we've started to remove the incoherent beam. And Kaustubh described about incoherent beams a bit. You probably know this is where you're not using the phases of all the different antennae. You're basically just adding their powers together. But since all of those feeds are detecting the same signal at the same time, you can subtract that from the actual coherent beams, and you can remove a lot of the common mode signal that's seen by all your feeds. So what I'm showing here, this is time frequency data. You can see there's some strong interference. The chime band is quite noisy. But what I want you to see is this vertical striping. There's like some slight yellow-green striping. That's the original data. But if I switch back and forth, hopefully this is able to switch fast enough that you can see that those yellow striping, the vertical striping, almost completely goes away. And so that dramatically improves the red noise in our data and makes it significantly more sensitive to really slow pulsars. So that was really excellent work that Robert has done. But RFI, as you can see, was not really affected at all. This narrowband RFI is still a really big issue. That's one of the last things I want to bring up. We know RFI is a huge contaminant to our data, and it's only going to get worse, not better. And it can dramatically change the statistics in your data and gives you huge numbers of false positives. The other thing that's tricky is that with injections, which is one of my last slides I'm going to show about how I recommend to look at a lot of these things, it's very hard to simulate because it's hard to simulate real life RFI. You can do some things, but your simulated RFI is almost always better behaved than real RFI. So one of the things that we normally do is just excise it. So this is a plot from RFI Find in Presto, and the red points here just simply get zeroed out effectively in the data processing. And the point a lot of students often forget about this is that this is often not as bad as you think, because our sensitivity goes as the square root of the bandwidth and the square root of time. So for instance, this example here, where we're having to remove 20% of our band due to the strong interference, given that it's the square root of the bandwidth as our sensitivity, we're only losing about 10% of our overall sensitivity. And then you can also use a bunch of other advantages that RFI is not typically dispersed, and it's the same in simultaneous beams. So kind of as a summary that I want to leave you with is just about testing this stuff. So I highly recommend people use well-developed and tested codes, and then test and test and test these again. And test for signals, test for noise, and test them quantitatively. You can use pure noise and perfect signals, and you should be able to predict the recovery of your pipelines with pure noise and perfect signals. But then it's even better to test that into real data, because the problem with real data is that there's red noise, there's RFI, stuff like that. And that's why injecting fake signals into real data is one of the very, very best ways to test these pipelines. And you want to inject as close to the beginning of the pipeline as absolutely possible. And it also, what this does is if you do a ton of injections, it also lets you compute as a function of all your different parameter space you're searching over, how efficient your search is going to be. And then the last thing is just make sure, really, please make your code available, put it on GitHub, encourage people to use it, ask them to cite it, which they will, put it on ASCL so you'll get citations, because others use this and they test it and they'll cite you. I see way too much code that people are not sharing nowadays because they've made their new pipeline and they say, oh, my code's not good enough, it's not pretty enough, someday I'll release it. Release it now, make it available, and tell people about it. And then it's just my last slide just to show you some citations about some of the things I talked about. Here's two amazing papers about how Chime FRB does injections. And if you don't know how this methodology works of injections, it's way beyond this talk. I highly recommend that you look at these two really, really beautiful papers to show how this all works. And keep an eye out for the new Chime FRB catalog paper. Catalog paper number 2 with over 3,000 FRBs is coming very soon, and a paper on CHAMPS injections by my student Ray. And I'll end there. Thank you.
Thanks very much, Scott. Very nice talk. Questions from the audience? Yeah, question.
Thank you, Scott. I have some point that I think you probably lightly touched upon. So on the scalloping issues, do you want to say something on the finite? Yeah, thank you.
Yeah, so scalloping obviously is a very important point for FFT-based searches. The very quick thing for people who don't know what scalloping is, let's say you have 1,024 bins in your time series. If you take the Fourier transform, because of the Nyquist theorem, you get 512 frequencies, but you can have any frequency in your time series. It doesn't have to exactly match one of the 512 bins. So that causes scalloping. Scalloping is something that you have to take into account. And so on average, you're going to lose signal due to scalloping. And so the nice thing about injections, so in the CHIME survey, for the CHIME, the CHAMP survey, our detailed injection pipeline exactly accounts for scalloping in every instance for every harmonic, and it plays a big role. You lose 20 to 40% sensitivity from an FFT-based search due to scalloping. But there are scalloping effects in other algorithms as well. Like it's not completely gone in like even an FFA-based search. It's better, but unless you highly oversample your FFA, which is the fast folding algorithm, you still have scalloping effects even there.
Hey, Scott. Thanks for a really nice talk. I have a question about the plot that you showed where you lose power at the higher frequencies because of dispersion. I saw that there was a little bit of a dip even at the, lower frequencies for some of those plots. Can you explain what that is?
Yeah, this is really quite recent work. I think this just could be just a noise fluctuation because we didn't do, for making this particular plot, Ray didn't do a whole ton of injections. But yeah, no, this is interesting. This is something we're looking into. I do not quite understand how the blue lines are dipping right here. And it is at a loss of something like, 10 to 20% over this regime. And this is right in the regime where we're trying to find most of our pulsars. So yeah, we're looking for all of these things. And this is why you really have to test. Like there was no expectation that anything like this should be there. Presto has been tested hugely, and this is using Presto dedispersion. So we're not quite sure exactly. Yeah, so we're looking into it.
All right, thanks.
Questions from online participants, if any? Further questions from the audience, comments? Okay, if not, let's thank Scott and the rest of the speakers of the morning session. We break for coffee now and reconvene at 11:30.